In these notes, we're going to talk about special cases that occur when solving systems by substitution. With substitution, remember, we always want an x equals or a y equals equation, or we want to make an x equals or y equals equation, right? We want some of the equations, or one of the equations, to look like this or that, okay? However, if you look at this example, both of them have a y equals equation. So which one do you use? And it's actually, you can choose either or to substitute the other one. I'm going to take this top one just because it's the first y equals equation. It's not a number, but it is a variable, and that's what y is. So we're going to replace that equation, 3x plus 14, that is equal to y, and we're going to substitute it in for this y in the bottom equation. Okay. In doing that, the 3x plus 14, I'm going to put it in parentheses just so you know that that's the substituted value for y. But it's all alone on the left side, and that's equal to negative 8x minus 19. Now if we look at these two equations, now that they're molded into one, we have to solve for x because the only variable left is x. However, we can't just start combining like terms and saying 3 minus 8. That can't happen. Like, that's a no-go, right? So what we want to do is get all of the variables like x to one side of the equation and all the constants like 14 to the other side of the equation. So I'm going to do that in two steps. You may want to do it in one step without doing it, but I want to move the x's across the equal sign to combine them with a like term that is 3x. We can't just combine them. We have to add this 8x across and use our algebra skills. So that would look like 3x plus 8x is 11x. We still have the 14 equals just a negative 19 on the right side. But now that there is an x on this side, we want to move the non-x, the constant term, 14, to the other side. So we're going to do that by subtracting 14. That gives us 11x on the left equals a negative 19 minus 14 is a negative 33. Divide away the 11, divide away the 11, and x is equal to negative 3. We're good. We like that. Okay? But we still don't have all terms. Remember, the solution to a system is an x comma y. That's a bad y right there. Okay, so we still need that y variable. Now normally we just substitute that x back into the y equation, and really what you can do is substitute that back into, because both of them are y, I can substitute into the top equation or the bottom equation. It does not matter which equation we substitute that negative 3 back in for to find the y that we're still looking for. I'm just out of like ease, I think 3x, because it's a positive, may be easier than worked with the negative 8x plus 14, and 14 is maybe a smaller number than 19, so I'm going to do it in the top equation. So we're going to use the equation y is equal to 3x plus 14, and we're going to take the x equals negative 3 value and substitute it in for x. So y is equal to 3 times x, which is now negative 3, plus 14. 3 times negative 3 is negative 9. Add 14, and we get 5. So y is equal to 5. So as a solution, x, negative 3, y, 5. Now I'm going to we did the top equation to the bottom equation, so over here I'm going to take the bottom equation and put it into the top equation, and I'm going to show you that you can still do it either way and you'll get an answer. Okay? I could have put this negative 3 into this bottom equation, you would have still solved for and gotten 5 on the end. Okay? But let's do this. I'm going to take this bottom equation, that's y, and substitute it in for the y in the top. So this 6x minus 16 is going to go on the top. So what that looks like is a 6x minus 16 is equal to the rest of the equation, 8x minus 20. Now in this case, if I subtracted the 8x over, like I added the 8x over here, I would get a negative number when I subtract 8 from 6. So I'm going to try and keep everything positive, and I want to move my 6x to the other side. You don't have to do that, but it's your choice. So let's subtract that 6x, subtract 6x, and get the x's by themselves. So now negative 16 on the left is equal to only a 2x minus 20. The 20 needs to move to the other side. So let's add 20 to both sides. I like that because now we're getting a positive number on the left. Negative 16 plus 20 is a positive 4. Equals the 2x. Divide away the 2, divide away the 2. And 2 is equal to your x value. Okay. Again, we need a y because we have the x. So I'm going to put this back into, again, you can put it into either the top or the bottom. It does not matter. Because I did it into the top equation this time, I'm just going to show you that you can do it in the bottom equation. We're going to take the bottom equation, y is equal to 6x minus 16. Put that 2 in, that is x. And let's do the math. 2 times 2 minus 16 is 4 minus 16, which equals negative 12. So our y value is negative 12. Oh, you know what? I did my math wrong. I carried this 6 and I changed it to a 2. This should have been 6 times 2. 6 times 2 is 12. 12 minus 16 is negative 4. So I made a mistake, caught it. Okay, that's 612, boom, negative 4. X is 2, y is negative 4. So the solution to negative 4. That's our answer. Okay. So these are the special cases when we have more than just an x equals or just a y equals. We have both. We have, in this case, both of them are y equals equations. Okay. Now, the true special cases where you do not have a solution or one solution scenario are stuff that we've talked about when graphing. If you remember graphing, the point of intersection is the solution, but there are other scenarios where you have parallel lines where there's no solution, and the scenario where you have a line and then you graph another line right on top of it, or you have an infinite number of solutions. We're talking about these two special cases here. So there are two special cases for a system of equation, like we're talking here, no solutions and infinite solutions. And those two cases are, and I'm just going to write that, no solutions and an infinite number of solutions. Now you can say infinitely many, but I'm going to shortcut infinite solutions. Those are the two special cases that you could get. Okay, and they look way different in the long run in the answer than these two look like in all the other solving systems by substitution problems that we have done up to this point. So let's jump to number 3, the example 3. So we're going to determine which special case this is, no solution or infinite solutions. Right away you see that y is all by itself, so that's the substitution that we're going to do. And we're going to take that 5x plus 2 and put it into that 3. So 3 times 5x plus 2. Then there's a minus 15x equals negative 1. With this 3 times y up here, now we need to distribute that 3 into the new equation that is y. So now we have a 15x plus 6. We subtract 15x minus 1. Before we do anything here with the solving, you have two like terms. We have a positive 15x and a negative 15x. Okay? Well, 15 minus 15 is 0, so we have 0 x's, and then plus 6 equals negative 1. But really, this 0, and I'm going to write the word 0 here, doesn't do anything. 0x means 0 times x. Well, 0 times x is just 0, and 0 plus 6 is just 6. So in the long run, this left side, when we simplify everything, gets just 6. The x terms, in a sense, positive 15 and negative 15, cancel each other out. They eliminate, and so you're left with, on the left side, 6 equals negative 1. Now, if you remember when we check solutions, 6 equals negative 1 is not a true statement because the left side is not equal to the right side. So this is not true. Like, in no way is this a true statement. Okay? 6 will never equal -1. So in the scenario that this is not true, this is one of the special cases. And I bet you could guess a not true statement goes with no solutions. So no solutions. That is the answer to this problem, because the variables eliminate and we get a 6 equals -1. That would, if graphed, looks like two parallel lines. Similarly, number 4 has x equals instead of y equals, so we're going to take the x equals equation and we're going to substitute that into where the x is in the other equation. So let's do that real quick. -10y stays -2. I almost forgot the -2. -2 times that -5y plus 11, and then the rest of the equation is equal to -22. If we distribute the -2, remember, when you carry, you're carrying the -2 to both the -5 and the -11. So we have now a -10y, -2 times -5, two negatives when multiplying makes a positive, positive 10y, and -2 times the -11 is -22, equals -22. Again, before we start doing any algebra, you can see that the two like terms, this is a -10x, or 10y, and a positive 10y, that would equal 0y. But just like the zeros over here, these two are opposites or inverse. They cancel out, and so we don't have those there. We just have a -22. So imagine those just go away, and the left side is -22, and the right side is 22. Now, unlike this 6 and -1, this is a true statement. I'm going to say this is true. Okay? It's true because -22 on the left is equal to -22 on the right. We like that. That's my check. Boom. So the special case, if you eliminate all the variables, but the remainder is equal left and right, that's an infinite solution scenario. So our answer here is infinite solutions. And to finish out the summary of this, I will zoom out and let's just kind of, so when we had a not true statement, it was no solutions. When we had a true statement at the end, it was infinite solutions. So to summarize, if all variables are eliminated in the substitution process, this eliminates with that eliminates with that. And there are the scenarios, for example, 7 equals 7, -3 equals -3, 11 equals 11. That's something like this. These are true statements. For these problems, we have an infinite solutions possibility. In the case that you get a statement that's not true, and these are some examples, where the left is not equal to the right, that is a no solutions scenario. So you can go and work on the worksheet that's titled Solving Systems by Substitution Special Cases.